Michael. Okay, so more hand raising. Thank you guys for joining me after lunch on the final day. How many of you have heard the statement, correlation is not causation? Okay, so everyone. Now, how many people have estimated a causal impact? All right, totally what I expected. So what that shows me is that we know everyone hears, that correlation is not the end all and be all, and causation is really important. But in reality, it isn't done in practice so much. And one reason for that is because it's difficult and it's really, really messy. So causal inference is the process of drawing a conclusion about a causal effect based on the occurrence of an event. And it's difficult because if you thought data munging was dirty, if you thought one-hot encoding was difficult, if you thought standardizing your variables could be really ugly, well, I have a treat for you because causal inference is really not sexy. It's a branch of data science that's not sexy, but it's incredibly important, and hopefully by the end of today's talk, I'll have proven that to you. So let's go over some examples. I want to bring this back to the real world and really give you a sense of some of the questions that we face in the tech industry at Silicon Valley, not just at Yelp, but across the board. Causal inference is able to give you the causal impact of things. So one can answer potential questions like, what's the monetary value of an additional user hour? We can actually get that actual numerical effect. Or how is advertiser churn affected by switching to a new sales model? When you have a new sales model, you might expect some advertiser churn, and we can measure that impact with causal inference. Or if you reroute your users from the mobile site to downloading the app, how does that increase the page views on your website? So a lot of these questions are only answerable by causal inference. Okay, so the purpose of causality, establishing definitively that a feature X causes an outcome Y, instead of just trending along with it. So why don't we just establish correlation? Correlation is often enough if you want to do prediction. We've all seen ML models. No one ever has to talk about causality. You can predict and forecast the future up to however many days with correlation alone without knowing the underlying dynamics that govern the causal flow of the variables. So if you're just doing prediction, it might be enough not to worry about causal inference. Or if you want to understand general trends in your data and overlaying heuristics, you may not need causal inference. You don't need to invest in all of this. Also, you could just conduct an A/B experiment. So an A/B experiment, an A/B test, its purpose is to establish causality. So a perfect A/B experiment done well does the causality for you. So in those cases, you don't need to do causal inference separately. It's not always possible, though. And in fact, in most cases, it's not possible. It's very difficult to have a perfect, clean A/B test, especially when you're scaling up your enterprise. Okay, so let's first look at A/B testing, though. What would an A/B test look like, and how would we determine causality from that? So here I have two screenshots of a potential home screen that a user would land on in the Yelp app. And you can see that some users would get the control home screen on the left-hand side, and some users would see the treatment, the new application home screen on the right-hand side. So if we want to know the effect of how this new home screen affected our user behavior, we could just have different users see different things and then try to get the effect that way, see how they behave differently. Now, we can already see a few problems with this, hopefully. There are slight problems with the A/B test this is not a real A/B test that we did, by the way. But so a lot of things are changing on the right-hand side. Not only have all the buttons become different icons, but we've added an add photo icon at the top left. We've added an add tip. There are some ads there, and there's a bottom icons as well. Okay, so if you want to know the effect of add photos alone, you're not going to get that from this A/B experiment. All you're going to get is the effect of this whole new layout as opposed to the previous status quo layout. Okay, so let's say that here we find out we have a 2% lift in some metric Y. This is something we do all the time. We run hundreds of A/B tests all the time, and so do all the big tech companies, Amazon, Google, all of them. Okay, so great. In this particular case, if we've done the A/B test correctly, then we already know the causal impact of the new home screen. It's a 2% lift in metric Y. Okay, but we can't always do an A/B test. There are a lot of issues with that. For example, if you have a historic data and you want to look at something that happened, a treatment or an event that occurred historically, you can't go back and then cohort your users into different cohorts and test that. You have to just rely on the historic data and establish causality that way. Or, you know, as I see a lot, there are a lot of imperfect experiments. The example I just gave was exactly one of those. A lot of things were changing there. So if you want to determine what change exactly caused the 2% lift in metric Y, it's going to be difficult to tease that out with the experiment we just ran. Okay, so in perfect experiments, we see non-random cohorting. Sometimes users are not perfectly randomly split into treatment and control cohorts, so the experiment is not valid. There are also other confounding changes. A lot of tech companies run a lot of experiments together, and we try to layer it to have different salts so that they don't compromise each other, but it's not always perfect, and sometimes experiments run together, and then it's difficult to isolate the effect of one particular change. Also, there's causality from actions we can't control. So if I want to look at user behavior and how that drives one of my business outcomes, I can't go out there and force the user to perform certain actions. Right? So I can't have a controlled environment for something that happens in the wild. And so if you want to look at the effect of something that happens beyond your control, you're going to have to rely on causal inference. Okay. In addition, it's not always desirable. We have that was a big interface change that could potentially have a huge hit on the user experience. There are some changes we've made that have had hits, and you want to mitigate that. So sometimes you don't want to scale out a big change on the platform. Also, some tests may not be ethical or fair. You can imagine doing some experiments on your sales reps or some of your users that would not necessarily be acceptable. Okay. So the idea is that if we want to lever a targeted business action in order to change an outcome, we do have to determine that the correlation is causal. Just having two variables trend together does not mean that we can lever one of the variables to push another outcome. Okay. So here's an example for that. Imagine that we see an X% increase in push notifications, or we implement an X% increase in push notifications. So that, I'm going to have some terminology, we're going to call that the treatment effect. And we're going to see that causes a Y% lift in the click-through rate. Click-through rate is a big buzzword in Silicon Valley. We talk about that a lot because websites care about click-through rates. Okay, so if we know that it's causal, then what we can do is we can actually use push notifications to reach a certain desired click-through rate that we want. But if the relationship is not causal, then no amount of changing the push notifications is necessarily going to lever click-through rate. Okay. It also helps us to properly attribute outcomes to certain business decisions, right? So if we're, investing in a bunch of different initiatives at our business and we see that the business is doing well, we need to know which one of those is actually causing the business to do well in order to invest further in the thing that's leading to that. So we want to properly attribute success to certain business initiatives. Okay, so as Michael mentioned, real-world data is really, really, really messy. And when you perform causal inference on this messy data, it's a pain. And I suspect that's a huge reason why a lot of people stay away from causal inference. It's not like an ML model. We may think ML model is difficult. Have to do some standardization, for a neural net, have to make all the pictures the same size, do some resizing, rescaling, whatever. But this is really different because we're going to have to layer on a ton of assumptions in order to eke out a tiny bit, just one answer. Okay, so I'm going to walk through different data types today, and they're going to include longitudinal data, otherwise known as panel data, cross-sectional data, time series with a lot of periodicity. We're going to have to be able to deal with all of these data types. Selection bias as a factor, a bunch of confounding variables, and reverse causality as well. So these are all issues that we have to face when we do causal inference. Okay, so at the heart of any causal inference problem is determining the counterfactual. We want to know what would have happened to the treatment cohort if they had never been treated. So let me translate that back into real-world terminology. What would have happened to the people who didn't see the new app home screen? What would have happened to the people who did see the new app screen if they had not seen it instead? So we're determining a counterfactual. And this, in general, in machine learning and deep learning is also a thing that we care a lot about. So in general, determining the counterfactual is a big headache for all of us. So this just doesn't just apply to causal inference. So if I can tease out what would have happened, then I can measure the size of the impact of what did happen, and I can get a sense of the return on our investment. All right, so first things first. Before we actually get started with some of the tooling that I'm going to introduce, we need to check a few things. And these things are going to keep coming back throughout the presentation. So I'm going to talk about selection bias. We're going to talk about identifying some natural experiments and identifying confounders. So no matter what inference technique you use, you're not going to get away from these three things. All right, so I'm going to keep using actual examples that we see, in this online space. So one question we ask is, does app usage actually increase user engagement? So that's a pretty important question for any platform that has users and rely on the users to generate content and as part of the business model. There's only one problem here, which is in the universe of people, right? In the general population, they may be infrequent Yelp users. But of the users that have the app, they're probably more likely to be extremely engaged Yelp users. So they're different. They're fundamentally different from the general population. So I can't easily compare those people. Or users with the Yelp app pre-installed. Okay, so what we need to do before we do any causal inference is we need to check whether there is selection bias. So what I would do is I want to see, okay, so the treatment in this case is having the app. So I want to see, is the treatment equally distributed across my different cohorts? So my cohorts are people with the app, that's the treatment cohort, and people without the Yelp app. That's the control cohort. And I'm going to be comparing the effect of the app that way. And now, as we can see, if I look at these are not real numbers, I can't show real numbers, but if I look at the pre-treatment period, if I look at the pre-analysis period, I can see that, yeah, in fact, users with the app were more engaged than users without the app. So how can I just subtract the effects of the app on those two groups? I can't just do that. I have to do some stuff beforehand to make sure that the treatment and control cohorts are comparable. So we do that amongst many other techniques. We do that most commonly using matching. So in this example, again, the treatment cohort are the users that have the app installed, and the control cohort are those without the app. And so we have this general population. But what we want in our causal inference analysis is to take away the people who definitely would have had the app, or people who had no chance of ever downloading the Yelp app. Okay, we want to have people as comparable as possible. In some circles, it's known as a twin study. We find a twin for every control individual. We find a twin in the treatment cohort. Okay. So then the question becomes, how do I know the likelihood that they would have downloaded the app, right? If I know the likelihood that you would have downloaded the app, we can just compare you and match you like that. So the first step is to determine that likelihood. So there are many ways to do it, and one way is a propensity score matching method. So the propensity score matching method is based on a logistic regression. So first, we model your likelihood of undergoing treatment, in this case, installing the app. Okay, and so of course, with any sort of linear modeling, you have to be very careful, and it's more of an art than anything else. And so there are a few packages available for this, but they tend to be, you'll see throughout this talk that a lot of the causal inference packaging within Python is underdeveloped. And so we do rely on a lot of UDFs, and we do rely on a lot of individual contributors to contribute these modules. So there is a causal inference package authored by an individual developer, Lawrence Wong. It actually is very good to use, but since the propensity matching is based on a simple logistic regression, one can implement a logistic regression via either scikit-learn or stats models. So either way. Okay, and other matching methods, we can use clustering methods such as nearest neighbors, readily available in scikit-learn. So let me just show you what the implementation would look like with the causal inference package. Okay, so here, how we would model this, model a user's likelihood of installing the app undergoing treatment, is you get a set of covariates, X variables, that determine selection into having the app or not. So in this particular example, one can imagine, okay, what makes you likely to have the Yelp app? Well, if you're a mobile user, a heavy mobile user in general, so if we had data on mobile usage, if you have a lot of other apps, if you have the app pre-installed on certain Android phones that we have contracts with, those are all things that make you likely to have the app. And then we model your likelihood, and once we have everyone's likelihood, we match them up. And we only keep the people, we keep a pool of people that are similar. Okay, so you essentially you start up a causal model object and then fit it and then get a propensity calculation. And then you have to do the matching yourself after that. So this just gives you the likelihood. Okay, so did we correct for it? Well, this is an example of something I did, the before and after of a likelihood of undergoing treatment when I corrected for the selection bias. And you can see that before I did the matching, the treatment cohort was much more likely to take whatever action the treatment was. In our case, it was not the installation of the app. But in our example, it's the installation of the app. So they were fundamentally different. The people in the different groups were very different from each other. But afterwards, I took out all the people who were not similar to each other. I restricted it to a subset of the sample, and I'm left with a much better and more comparable pool of people. Okay, so natural experiments. We also want to look for natural experiments. This is a great way of getting exogeneity, which is essentially what you want in any causal analysis. So natural experiments are interventions that occur outside of a controlled setting, so anything that happens naturally. And so it has to happen naturally, and the treatment has to differentially affect different groups of people so that we can see the different impact on the different groups. Okay, one example for us is something I mentioned before, which is that the Yelp app comes pre-installed in certain Android phones. So I don't have to, if I'm looking at the impact of the app being on your phone, I don't need to look just for people who manually went and installed the app. I can look at people who had the app naturally on their phones. So they didn't select into the treatment group or the control group. Okay, so that's a natural experiment. If you have one of those, then it's much easier to determine causality. All right, we also have to very carefully identify all the confounding features. So in this case, we are looking at, again, having the app and its effect on user engagement, so their likelihood of coming back onto the app. And what if we're forgetting something? What if we're forgetting another variable z that's associated with both things? I already mentioned some of those potential factors, those confounding factors, right? The fact that if I don't account for the fact that some people have the app pre-installed, if I don't account for the fact that some people are just heavy mobile users, then I'm going to have a really biased estimate of the impact of x on y. I'm going to capture the effect of z when I estimate the impact of x on y. Okay, so we finally get to some techniques, and these are the 5 techniques that I'm going to go over, and I'm going to also talk about the tooling that's available for this, and some of the things you can do when tooling is not available. So it turns out these are all based on statistical methods, so even when packages are not available, we can get a little lower, and you can actually build things from the ground up. Okay, so the first thing, let's start off easy. Start off with a standard regression. So the counterfactual in this case, if we look at the question, how does price affect ad sales? That's definitely something we care about. We care about whether our cost per click is going to affect ad sales. But when you do a simple regression, it's never simple when you're trying to get causality, because if you don't control for all the other potential confounding factors, your counterfactual cannot be established. The counterfactual is based on the assumption that we have accounted for all possible causes of ad sales. Okay, and this is one example in which both cost per click and the ad spend, which is the advertising budget of the companies, are really important indicators, predictors of ad sales. So if I only look at one of these dimensions and don't factor in the others, we're going to have some problems. Okay, so there's a lot of tools for regression. I'm sure you guys have seen some of them. In scikit-learn, we have the linear regression model and stats models. We have OLS as well as a ton of non-parametric regression tooling. And to do this, it's fairly simple. You know, we add NumPy column stack of our variables that we think determine the outcome. And then we just simply fit. So this relies on, I like to illustrate this even though it's a very simple thing, because it shows that unlike other machine learning models where we rely a lot on the machinery, here we really rely on you, the user, the data scientist, to have domain knowledge, to properly orchestrate, to properly model this behavior. We can't just rely on the neural net to find the patterns that we can't see. No, we have to see the patterns in advance and put them into the model. Otherwise, things will, you know, you're not going to get a good estimate. Okay, so another technique is Bayesian time series. I really like this, this fairly new package written by Google because it allows us to really lever time series data well. Okay, so Bayesian structural time series is based on the idea that we have control time series that can predict another time series. So it's related to Granger causality, which is a whole, you know, time series of variables that can then predict something else. So the question here is, how many additional daily clicks were generated by an ad campaign? Net of cannibalization. What does net of cannibalization mean? You can imagine that I have an ad for a business and the user clicks on it, but actually that user might have clicked on the business page anyway. So I have to take away the effect of them potentially clicking on it anyway. I can't attribute that to the success of the ad campaign. That would have been an organic user. Okay, so this is hopefully going to allow us to do that. So what we have here, is there a laser beam thing? No, it's not. Okay, no laser, that's all right. So we have the outcome variable y. All right, so the second vertical dotted line is going to be when the ad campaign started. So before that, we're going to fit the time series model on the observations of y prior to when the treatment occurs at that second dotted line. So we're going to have x1 and x2 as time series that determine y, and we're going to fit the model to the pre-treatment time frame. And then post-treatment, so everything after that second vertical dotted line, we're going to determine the counterfactual. We're going to estimate what would have happened had we not had the treatment. Okay, so we're going to estimate what would have happened if the ad campaign had never happened. All right, so the dotted line, the dotted blue line on the right-hand side is our estimate based on the time series, the red and green time series, and that's our estimate of what would have happened. So this assumes a lot of things. It assumes that the time series x1 and x2 were not impacted by the ad campaign. They have to be exogenous. And we have to assume that they have the same exact relationship with the outcome variable y, in this case, daily ad clicks, before and after the treatment. So as I mentioned before, a lot of strong assumptions to do a lot of things here. And in order to model the time series properly, we have to do local linear regression. We have to do, you know, some time series prediction with various periodicities. There's a lot of heavy tooling behind this. But luckily, we have some help because we have the package that I'll talk about in a bit. So what this allows us to do then is it allows us to get, okay, at the top graph, we're modeling US ad clicks on a daily basis. And then we get a prediction of what the ad clicks would have been on a daily basis had we not had the ad campaign. So every single day, we can measure the difference in how much our ad campaign contributed to ad clicks. And then in the lower graph, what you get is a cumulative impact. So for something like an ad campaign, you don't want the effect of one day. You don't want to say what happened on exactly 30 days after the ad campaign started. You want to have a period. So in this particular case, we're looking at a 7-week window after the ad campaign started, and we want to see what was the total amount of clicks that were generated by this ad campaign. So this model allows us to get this cumulative effect across time. And so luckily, this, you know, a lot of tooling goes into this. Thank God our friends at Google, our good friends at Google, created this package called the Causal Impact package. They all have very clever names: causal inference, causal impact. Okay, so the Google Causal Impact package is unfortunately solely written in R, but lucky for us, we do have an RPy2 connector to Python such that you can write R code straight into a Jupyter notebook. Of course, it does require you to unfortunately know how to write in R code. So that's potentially a problem. But there's also, again, we're saved by our individual developers here. So there's this developer named Jamal, can't pronounce the last name, who ported the R causal impact package from R into Python. Okay, so this is, again, an alpha tested. This is not, I don't necessarily, I have not rigorously tested this, but so far it looks good. In my few tests, it looks good. So what you do is you set up a pre-period date-time list. You have a post-period date-time list, and then you determine some control time series you want, x1 and x2, and you simply run the causal impact package. And it does all of the heavy lifting under the hood. It's doing a bunch of non-parametric stuff. It's doing ARIMA. It's doing Fourier. It's doing all of that. You don't even have to do it. That's the coolest part. But if you don't trust this individual contributor and you don't want to write in R code, there's another solution. You could use Facebook's Prophet, which is a very, very, very powerful time series forecasting tool. I highly recommend it. But it does require you to know what you're doing in terms of modeling the time series itself, modeling the various periodicities, weekly cyclicality, monthly cyclicality, daily cyclicality. And then you can get the prediction and determine the difference between the prediction and the observed effect yourself. So you can figure it out yourself if you want. It gives you a lot more control over what's going on in the back end. Okay, so a lot of ways around that. All right, another method that's used a lot in statistics is what's known as difference in differences. Okay, so here is where we already know that we have some problems. We already know that people are fundamental, the control group and the treatment group are fundamentally different. We realize the selection bias, and we're going to just correct for it naturally within the technique itself. So here the question is, I like to give you examples of all the different questions we face. So did our new sales model, we switch out sales models once in a while. Our sales models are built on machine learning predictive models, and we switch them out from time to time and update them. Did our new sales model affect our sales reps' call behavior? Okay, we put out a new sales model. Did that result in them calling more or less people, or no effect at all? Okay, so here we know that, hey, some sales reps are, call more people than other sales reps. So we know that there might have been some differences in our control and treatment cohorts to begin with. So what we do is, in order to determine the effect of our new sales model, in other words, the intervention, we're going to assume something very strong, which is known as the parallel trends assumption, which is that, hey, we know that the sales reps have the same slope, have a similar relationship between their slopes before and after the treatment. So we're going to estimate the counterfactual by assuming that same relationship in their slopes would have been maintained had one of them not seen the new sales model. So one of them got the new sales model, one of them didn't get this new sales model. In this case, in this example, the better performing reps in terms of call volume got the new sales model first. So if we want to determine that effect by getting rid of the selection bias, what you look at the change in the slope relative to your estimated counterfactual. Okay. Now something that we face, and a lot of tech companies face, is things are not deployed simultaneously. If you have a new model or if you have a new feature on your site, you don't necessarily roll it out, what we call roll it out to 100% of our users immediately. We might roll it in waves. Similarly here, our new sales model, we didn't roll it out to our sales reps all at once, right? We're testing it, so we roll it out in waves. So here's an example where the intervention is occurring at different times. So sales reps 1 through 3 are seeing different before and after periods. So we have to do a little bit of manipulation. As I told you, tons of manipulation is going into trying to eke out this little one number impact. So what we can do is look at a certain set of days before and after they got the intervention and simply cut them off that way. So even though they got the intervention at different times in the calendar year, we're going to just look at each of them and 30 days prior and 30 days after they got the intervention. They saw this new sales model. Okay, so some tools for difference in difference. It's actually pretty easy to implement. This is one of the nicer and easier ones to implement that's also very powerful because it had selection bias correction built into the model. All you have to do is implement a standard linear regression with an interaction between your treatment and the cohort group. That's all you have to do. And the coefficient estimate on the interaction t times x, that's going to be your impact. Okay, so pretty standard. You can do that with a simple regression. If you want to do what I talked about in terms of matching across time intervals, those are custom functions, but those are easily done with date-time functionality within pandas and NumPy. So I always implement them manually because there's no package for that. Okay. We also have instrumental variables. Okay, so here's a scenario that we've seen. How does signing up for cashback, Yelp has something called cashback, by the way, if you guys want to sign up. If you check in at certain restaurants, you can get some cash back. I get 10% off my meals all the time as a result of this. So how does signing up for cashback affect the activity of a user? Okay, so that sounds like we would want to know that, especially the cashback team. They want to know how it's affecting the activity of the user. There's just one problem, though. Users that are more active are more likely to sign up for a cashback. So that's known as simultaneity, right? It's where the arrows between x and y go in both directions. So in the cases of simultaneity, what you often want is an exogenous variable, a totally different variable that's correlated with your control variable, but not itself correlated with your outcome variable. So in this particular case, I could potentially look at signups for, third-party restaurant promo mailing lists, because those people are likely to have signed up for cashback, but not necessarily likely to have been a very active Yelp user. So you'd have to test this, of course. You have to test that a variable is a good instrument. And so there are a variety of tools that we have for instrumental variables, also known as IB. You can do a simple OLS to see if it was an effective instrument. So if X and Y are correlated, you can even just do a correlation analysis to see if X and Z were correlated, so that Z is a good instrument. There's also what's known as two-stage least squares, which is implemented in the stats model's GMM module. And this does it for you. You can put in your set of endogenous regressors. That's the ones you think are compromised. In this case, cashback, the likelihood of having cashback. Put in your exogenous regressors and put in a set of instruments for it. So in that case, signing up for some restaurant mailing list. Okay, and you simply fit it. And the IV2SLS model is also available via the linear models package, which is a separate, not as well tested as the stats models package. All right. So the final technique before we go into some of the pitfalls, regression discontinuity. Yelp has something called Yelp Elites. If you write enough reviews and you're a pretty engaged Yelp user, you can get elite status. You can become known as a Yelp elite, and then we fly you out to all sorts of events, and you get to go to a lot of parties, and you get a lot of Yelp perks, Yelp-style perks. Okay, so we can ask, we want to know, does becoming a Yelp elite cause users to actually write more reviews? Okay, do they become more engaged? Once we give this status symbol, are they going to contribute more to our community? The problem with that is you become a Yelp elite partially when you write a lot of reviews. So it's determining the treatment itself. Okay, so how do we account for that? Well, with regression discontinuity, we look at the pre-treatment and the post-treatment, and we graph them against each other. And we say, well, there was an arbitrary, we leverage this arbitrary cutoff at which point a user becomes a Yelp elite. I don't even know what the cutoff is. It's something, at some certain set of number of reviews, you can become a Yelp elite, and it's an arbitrary cutoff. So we say, if we look just locally at the users who were just below that cutoff and the users who were just above that cutoff, we can assume they're pretty similar. We can probably assume they're pretty similar. The difference between writing 49 reviews and 51 reviews, if the cutoff is at 50, like in this example, I don't know if it's actually 50. They're pretty similar users, so if we just look at them and how they behave differently after they become elite, then we can get at the effect of elite status. Okay, so again, not actual numbers. Just want to make sure. All right, so there are a lot of tools for regression discontinuity, and once again, this is a case in which R has a lot of the tooling. So we're going to have to use some connectors, or we're going to have to implement it ourselves. As I said again, it's not easy. Okay, so first we have to know that we can do a regression discontinuity. All of these techniques I've talked about require strong assumptions. So every time you apply a model, you have to make sure, if you're going to do, even in ML, if you're going to do a binary classification model, you better make sure that it's a binary problem. You have to make sure that the model fits the problem at hand. So here we need to make sure we can run a regression discontinuity. And to do that, we can do a McQuarrie density test, which sounds fancier than it is. It's actually just to look at whether there's a discontinuity in your distribution. So you can write a custom UDF for that because, again, the concept behind it is actually pretty simple. Or you can use R's DC density function, which has the McQuarrie density test within it, and connect it to Python via RPy2. We do a lot of RPy2 connecting. And then on top of that, the regression discontinuity design relies on a lot of non-parametric estimation. So you don't want to, in this example, I showed linear lines being fitted on both sides of the treatment, both pre and post-treatment, but they don't have to be linear, and in fact, they should not be linear. They should be non-parametric, and we could, for example, use the low-S regression technique to get non-parametric techniques so that they're non-linear lines on both sides. And then we're going to have to interpolate some points in between because there's going to be some sparsity there. So we can use scipy's interpolate function. Also, PyQt-fit is another package that has this non-parametric estimation and does it all very well and does the interpolation as well. So a lot of different options there. And if you want to go the parametric regression route, just estimating linear curves before and after, then you can just use stats models or scikit-learn. Okay, so this is just a summary of some of the packages that I've talked about. Of course, at the heart of it all, this is all implementable using NumPy and pandas. You don't have to rely on anything, you don't have to rely on nested dictionaries or anything like that. Okay, so there's a lot of pitfalls of causal inference as well. So I like this quote a lot from Andrew Lang. The statistician uses statistics as a drunken man uses lampposts for support rather than illumination. Great quote. Absolutely true. We got to always be suspicious of what we're finding, right? This is one of those things that's not. It's an art. So this is a problem I ran into. Someone asked me, by how much does an additional user vote? So on the Yelp platform, you can vote for things like if hours are correct. So a business, say, has, it says it accepts credit card, and a user can then vote no, that's not true. Or yes, I agree that that's actually true. Okay, so they were asking me, how much does an additional user vote on a business page increase page views? So that sounds great. It's like, yeah, so like we have people engaging on the platform, they're voting on other people's, on our attributes, and does it increase people coming to the traffic to the site? So this is the workflow of how that goes. We have user 1 going to the business page. User 1 makes a vote. Yes, this restaurant has amazing ambiance. It has a romantic ambiance. Then user 2 goes to the same page, and user 2 sees user 1's vote. Now, there's a problem here, right? Because the question was, once the user sees the vote, are they more likely to see the page? Are they more likely to view the page? But the problem with the actual flow is that the page view happens before the user actually sees the vote. So you can't actually make this sort of, you can't actually do this sort of analysis as it stands. You have to reframe the problem. Okay, so it's very much about understanding the nature, domain knowledge on your problem. There's also omitted variable bias. We ask ourselves, how much does an additional photo, when a user puts on a photo, does it affect the number of users that check in? The hypothesis being that, hey, if I see more photos on that biz page, then other people are going to see the photos and be like, oh, that's really great, and then they're going to go to the restaurant and they're going to check in. That's great, but what happens if we just look at the relationship of photos to check-ins? Right? There's a lot of things in between that are affecting it. So we can't just look at photos. We have to look at, if I want to look at the value of an additional photo, I have to know how many photos were already there, for example. I have to know how many reviews the business had. I have to know how old the business is, how long it's been around, because those are all things that are going to affect whether a user checks in at that business, regardless of whether or not there was an additional photo. So we have to be really careful of identifying all potential control variables. And so it's an interesting problem because you actually get to be super creative. It's not just about hyperparameter tuning. Whenever I do the other parts of my job, it's hyperparameter tuning, you run it into a program, but here you have to be very creative all the time. All right, and another thing is reverse causality. Does purchasing Yelp ads improve a business's performance? Obviously, all of our advertisers want to know this. If I purchase Yelp ads, is it going to improve my performance? Problem. If a business is doing well, it's also more likely to have ad expenditure budget, and it's also more likely to purchase Yelp ads. So we have causality going in two directions, and we need to potentially mitigate that. And one of the techniques I mentioned before, the instrumental variables, is something that helps with that. And finally, we have stratification. So here you see a plot where we have the overall population on the left-hand side. So in the overall population, X is negatively associated with Y. Some variable X is negatively associated with Y. But hey, then we group them into, say, men and women, or some other thing, app users and non-app users, and suddenly the trend reverses. Okay, this is known as Simpson's paradox, and it's actually more prevalent than you might think. So imagine that you're doing an analysis, and then you group your people into groups such that the trend actually reverses when compared to the general population. That's not good. You're not necessarily getting the correct intuition. And there are several ways in which this can happen. One way is if there's an unequal probability distribution of the treatment across your groups. So group A and group B had a different likelihood of undergoing the treatment to begin with. So it's still about selection bias. It's oftentimes about selection bias and removing selection bias in these problems. Okay, and another possibility is that we're looking at a specific snapshot in time and we're not looking at the overall aggregate effect across time. So you have to make sure that you look at the effect over the entire period rather than just a cross-section of specific points in time. Okay, and you should also check whether there was proper cohorting done before your analysis. Okay, and the final thing that I've worked with a lot is geospatial differences. We are actually a multinational company. A lot of people don't know that. Yelp is multinational. And in another lifetime, I was an international economist. So I looked at a lot of countries at once. And guess what? Users in one country are not going to have the same effect on an outcome as users in another country. It's incredibly important, time and time again, even in ML prediction models. When I put in geographical features, geospatial features, I find that they're hugely important to the predictive capacity. And in this case, incredibly important for determining causality and controlling for the differences that occur geographically. So there's many ways one can do this. One can have one-hot encoding for each of the different geographies, right? But you can imagine that the dimensionality would explode there. If you're a company like Google and you operate in every city almost in the entire world, if you want to control for every single city, my God, your dimension is just already in the millions. So one way you can do it is you can group regions together and one-hot encode that way. So you can group, either by state or by administrative census region, metro area, or country, if you're a big enough company. Or maybe you only care about your top 50 markets. So you can group according to your top 50 markets versus everyone else. There are all sorts of ways, whatever way, this is definitely about testing out a bunch of different things, but it's incredibly important to control for geospatial differences. All right, so in conclusion, causal inference is hard, and it's really unsexy, right? It's really unsexy. I made a lot of assumptions along the way, had to check for a lot of different things, control for tons of factors, tweak. It was very bespoke. There's no package where you can just toss your data in and it'll spit out the effect. You have to engineer it and massage it very carefully. But that's also what makes it fun. You get to be really creative, and you get to apply a lot of your domain knowledge to it. And no two people will do causal inference exactly the same. So you get a wide range of potential things. So there is some Python tooling available, but there's not much of it. So right now we're relying on a lot of individual developer contributions, which is, bless them, and I'm hopefully also going to contribute at some point that way. But my hope is that we're going to, in the future, pipe a lot more of R's functionality in this space over to Python. Otherwise, in the meantime, develop custom tooling, which requires a lot of fundamental understandings of what's going on in the background.